Hello, I'm Larry, one of the engineering liaisons with Buckeye Power Sales. Today we're going to discuss NFPA 110, which is the standard for emergency and standby power systems. We will look at the 2016 edition, but we will also reference earlier versions. This is not a code class. I am not one of the volunteers on the committee for NFPA 110, nor am I an authority having jurisdiction. However, we will look at NFPA 110 as far as lessons learned in preparing the emergency power supply system for its acceptance testing. So, why are we even talking about NFPA 110? For many states, the legislation body makes it a law to comply with NFPA 110. For example, in the state of Indiana, they adopted the 2012 International Fire Code, and that was effective December 1st, 2014. So why is the International Fire Code important? It includes NFPA 110 when it comes to the installation. And 110 is the standard for emergency and standby power systems. Now in the photo, I see Aurora Sheboygan Memorial Medical Center. Let's ask them what it means to have emergency backup power systems.
So one of the promises we've made to our community is that we're here 24/7 to provide that highest quality of care. And in order to do that, we need reliable power.
Power is critical to any hospital. Today's technology requires powered instrumentation. The advances in medicine have all been technological advances, and every one of those require a power source.
When we lose power, everything goes black, and it's just for a brief moment or two. And so in the last episode where we lost power, I mean, it's enough for me to stop in the hallway, everything's black, you take a deep breath in, and then the lights are back on. It's surprising how often there's power surges in the community, or again, a squirrel actually gets in a transformer and the lights go out for 20 minutes. In a residential setting, that may not be a big deal, but in a hospital, when we have actually so much of our technology and so much of our life-sustaining treatments depend on power, we absolutely need to be assured that that backup is there.
To know that you have a hospital, including now a neonatal intensive care unit, a full functioning emergency room, a full functioning intensive care unit, a full functioning operating room that can function 24/7 in the face of any crisis, I think is huge for any peace of mind of anyone in the community.
Our focus today is going to be Chapter 7 of the NFPA 110, and this is the installation and environmental considerations. There's a lot of sections to it, so we're going to focus in on particular sections of Chapter 7. Part of that will be the acceptance testing. We're going to build our own acronym so that it will help us remember specific areas of Chapter 7 so that we may design and install a reliable emergency power supply system. First, we'll be looking at the acceptance testing, and for that, we give a letter A. The next area of focus we'll look at is the fuel system, so let's put up the letter F. Thirdly, we'll look at location, location, location. So we'll put up the letter L. We'll also look at the exhaust system and the effect it has on reliability. So we'll put up the letter E. Finally, we'll go take a look at the cooling, heating, and ventilating system. And for that, we'll put up the letter C. And putting that all together, we have AFLAC, standing for Acceptance, Fuel, Location, Exhaust, Cooling. The NFPA 110 is not a design manual, but it is guidance to help us provide a more reliable system. And because of that, we'll see a couple examples where we could go beyond what's discussed, or maybe a more reliable system than what is discussed in NFPA 110. To get an overall look at NFPA 110, we'll go through the various chapters before we focus in on Chapter 7. Chapter 1 is Administration. Chapter 8 is Routine Maintenance and Operational Testing. John Penny, Service Manager in the Cleveland, Ohio area, gave an excellent presentation November 2014 to data center personnel on the routine maintenance and operational testing. This presentation is available on YouTube, and just search NFPA 110 generator reliability and you will be able to find John Pinney's 50-minute presentation.
We're going to talk about what the responsibility is of the operators at your facility and what is the maintenance requirements that need to be done to the equipment, the testing that there is to be done with the equipment. So we have weekly tests, monthly, quarterly, annual checks. We're going to talk about the documentation that you need to keep, and we're going to talk about the maintenance that needs to be done, everything monthly, annually, every 2 years, every 3 years, in addition to fuel management, monitoring, etc.
Next, we'll look at Chapter 2 and Chapter 3. Chapter 2 looks at reference publications. These are standards that shall be considered part of NFPA 110. For NFPA publications, there is NFPA 30, Flammable and Combustible Liquids Code, NFPA 37, Standard for the Installation and Use of Stationary Combustion Engines and Gas Turbines, NFPA 54, National Fuel Gas Code, NFPA 58, Liquefied Petroleum Gas Code, NFPA 70, the National Electrical Code, also known as NEC, NFPA 72, National Fire Alarm and Signaling Code, NFPA 99, Healthcare Facilities Code, and NFPA 780, the standard for the installation of lightning protection systems. Other publications referenced are the ASCE publications, American Society of Civil Engineers, which is ASCE/SEI7, which is minimum design loads for buildings and other structures. And other publications are the Merriam-Webster's Collegiate Dictionary. Chapter 3 covers definitions. Part of the definitions is the difference between the Emergency Power Supply, EPS, and the Emergency Power Supply System, EPSS. Here John Pinney does an excellent job in explaining the difference.
So we're going to start by talking about what is the EPSS, or the Emergency Power Supply System. It's comprised of the emergency power supply, which is the generator, but there's more than just the generator to your facility. There's the generator, there's the potentially multi-unit paralleling switchgear, you have transfer switches, you have batteries and battery chargers, you have potentially fire pumps and fire pump controls. The UPS is part of your EPSS, and you have remote annunciation or monitoring of the equipment.
In Chapter 4, we start defining emergency power supply systems by class, type, and level. We will begin with level, and that is involved with the installation, the performance, and the maintenance. For level, there are two levels, Level 1 and Level 2. Level 1 is loss of human life or serious injury. For those familiar with the National Electrical Code, this would be similar to Article 700, emergency systems. We typically think of these loads having to be up and available within 10 seconds after an outage. Level 2 is less critical to human life and safety. In the National Electrical Code, we can reference Article 701, legally required standby systems. And here we typically think of these loads as needing power within 60 seconds. The class is how long the emergency power supply can run before it has to be refueled. All these classes are rated in hours. There is a class 0.083, which I had to calculate to be 5 minutes. The next one, class 0.25, that one was a little easier for me, quarter of an hour or 15 minutes. There's also a class 2, which is for 2 hours, and I'm not sure if I've ever run across that. Class 6, 6 hours. Class 48 is 2 days, and often we hear of 96 hours runtime. That's a class X, where we can fill in the number of hours before the emergency power supplier has to be refueled. For type, this is how long the load can be without power. Now there are some loads that may take some time to reboot, and for this we may find it good to have an emergency power supply system in front of these loads so that they can basically ride through the outage. Those are a type U. There's also the type 10 seconds, and once again we think of these as life safety loads that have to be up and available, power to them within 10 seconds. The type 60, where those loads need power available to them within 1 minute. Type 120, where they have to have power available in 120 seconds or 2 minutes. And then there's also the type M, which would be perhaps your optional loads. There's no time limit. These are manually transferred over. So that is the level, class, and type as defined in Chapter 4. Chapter 5 covers the emergency power supply. There's a lot of information in this Chapter 5, and this is suitable for a discussion just on its own. But we're going to focus in on the AFLAC, the acceptance testing, the fuel systems, the location, the exhaust systems, and the cooling systems. Now some of the fuel systems will have day tanks. They'll also could have main tanks, piping systems. There's also the cooling systems. We will discuss that. Seen here is a remote radiator. What we are not going to cover today is the sizing of the emergency power supply as far as voltage dips, frequency dips, harmonics. We're not going to cover the starting system, the battery and the starter. We're not going to review the different batteries, battery heaters, battery trays, battery chargers, the different type of controls that are available, and we're not going to cover the remote annunciation. All this you will find in Chapter 5. The NFPA 110 covers transfer switch equipment in quite detail. Once again, this can be a topic all on its own, but briefly, in Chapter 6 is the bypass isolation switches, which are typically found in healthcare or data centers, those loads that are very critical and difficult to service and maintain. So let's focus in a little bit on transfer switches. There's basically two parts of the transfer switch. Typically on the door is the controller. I like to refer to that as the brains. And inside is the switching mechanism, the brawn. Here we see a bypass isolation switch with the doors open. So let's focus in on a bypass isolation transfer switch. Again, we see on the right the controls, but instead of switch, this is the bypass switch. We find the switch down below, and here we can service and maintain it, draw it out to a test position, and even take it out to be able to service and maintain it. So where does an automatic transfer switch fit in the emergency power supply system?
Most standby generator set systems are arranged to start automatically when the utility or primary power to the system load is interrupted. Interruption can be caused by numerous reasons, such as weather or equipment failure. Many standby systems are there to provide backup power to critical life and or economic load, such as hospitals and telecommunication stations. Typically, an automatic transfer switch, most frequently called an ATS, is used to transfer the load between the primary power source and the standby generator set. As this animation shows, utility power normally flows through the ATS contactor that connects the utility to the load. In a power failure, the utility contactor is de-energized. The control panel senses utility failure and signals the generator to start. When the generator has reached full voltage, the generator contactor is energized and closes the supply power to the load. The utility and generator contactors are mechanically and electrically interlocked to ensure only one power supply can be fed to the load.
So when I referred to the transfer switches as having brains and brawn, we see there's a lot of responsibility in the brains. Here it covers the logic, timers, communications, all the sensing. So this is where the decision making is done for the transfer switch. The brawn is the switch. The bypass isolation switch allows us to isolate the transfer switch. This diagram represents a bypass isolation switch where we can close a contact in parallel, allowing the transfer switch to be removed for service maintaining testing. Power is flowing from the left X down through the center of the transfer switch and down to the load represented by the X down there. The paralleling circuit is the red contactor that can be manually closed, allowing for parallel paths. And then the switch, the black in the center, can be isolated, showing the stabs there. We said earlier that NFPA 110 is not a design manual, and there are various options and ways to improve the reliability of an emergency power supply system. One is on your bypass isolation transfer switch. There's no comment regarding how do we service and maintain the controller. As we can see in this instruction manual, there is a harness disconnect plug that is energized, and in order to de-energize it, the load must be shut down. That is, the generator disabled and the normal breaker feeding the load be opened. The problem comes from the brains, or the controller needs to see the voltage. And here we see a diagram. On the right is the switch, on the left is the controller. We'll focus in that red rectangled area to get a little more detail. So here we see on this 480 volt system the phase A, B, C, and neutral going through the wires to the controller. Now the disconnect plug has various pins, and these pins have 480 volt potential between them, and these pins are closer than I can put my fingertips together. A solution is to isolate the A, B, C, and neutral wires and run these through a selector switch. The selector switch can then be mounted inside the enclosure where it is accessible to a trained technician. The instruction manual provides the proper procedures. Here we see a description of the logic disconnect switch and a sample specification. The client has the ability to service and maintain the controller without shutting down their most critical load. Now we will focus in on Chapter 7, the installation and environmental considerations. And once again, we won't cover the whole Chapter 7, but we'll focus in on our AFLAC. We are installing and maintaining emergency power supply systems for various needs. It could be flooding, tornadoes, earthquakes, vandalism, fires, storms, accidents. The transfer switches should be located as close as possible to the loads they serve. The emergency power supply must have adequate capacity or an automatic selective load pickup and shedding to be able to take care of first the level 1 loads indicated here in red, the level 2 loads in yellow, the optional loads located here in green, and when the normal power source is available, the emergency power supply is allowed to pick up other loads such as peak load shaving, internal voltage control, cogeneration, etc. This is indicated in the purple area.
Action.
To begin our AFLAC discussion, we'll focus in on L, location. This is a request for engineering design to replace an indoor generator set. In this case, the generator is no longer of sufficient size to take care of the proposed emergency building loads. Even though indoors, this generator was located in a sound deadening shelter. The location was also a problem because the exhaust fumes were coming back into the building. Finally, they say they would like this to be now relocated outdoors and have it visually screened, such as a wall, to make it architecturally pleasing. For emergency power supply located indoors, there needs to be a 2-hour firewall. This firewall could be of different construction. There should be some thought given as to what happens when the fire department enters. A masonry wall would just simply be cleaned with a fire hose put on it. However, a gypsum wall with the force of the fire hose can penetrate that wall within 10 seconds. For emergency power supply located indoors, there should be some thought given as to the door into the room. Due to the air pressure, it could be very difficult to open a door that does not open into the emergency power supply room.
Emergency equipment must be located as to minimize the hazards that might cause complete failure due to flooding, icing, fires, icing, or vandalism. I was in the WorldCom building right next to the World Trade Center about a few months after the World Trade, maybe less than a year after the World Trade Center went down. And the WorldCom building, I think this is probably like around a 70-story building. It was now turned off. No power to the building. What happened was when the World Trade Center went down, had all the fires, I think they ran fire hoses in there probably for 6 months, okay, trying to stop the smoldering in there. It filled up the first 3 floors of the basement of the WorldCom, and that's where they had the emergency generators.
And that's where they had the emergency generators. New York has gone ahead and changed the code as to location of an emergency power supply system, so always check local codes during the early design phase.
Essential building facilities such as hospitals, emergency shelters, water treatment plants, they all require that their mechanical and electrical components have IBC certification. The International Building Code was developed by the International Code Council, and in the code it says that non-structural components must, in addition to structurally withstand an earthquake, must maintain operability after the earthquake as well.
When the unit is shaken in the triaxial environment, it is seeing forces from every direction. It's forces from front to back, side to side, and top to bottom. So it's simulating, kind of a worst case earthquake event.
For outdoor generators, there could be the need to design for winter environments. A snow enclosure to keep snow from being brought into the generator set while running. Part of that is motorized dampers for the exhaust and the intake sides, as well as heaters. This package is designed to maintain 40 degrees Fahrenheit inside the enclosure.
Action.
Now we'll go back to our AFLAC and look at C, cooling. There are a number of design considerations when ventilating an emergency power supply. This is the amount of airflow, potential heat sources, how to remove the heat from the room, and what pressure drops are acceptable for ventilating. A lot of information can be found right on the manufacturer's data sheets. Here we see the radiator airflow, the combustion airflow, the radiated heat load from the emergency power supply, and the maximum allowed airflow pressure drop through the ventilation supply into the room and through the ventilation discharge from the radiator. To help in finding the minimum dimensions allowed for an internal generator set, there are various sizing programs available. Here's an example of a plan view of an emergency power supply, and from here we can see the minimum width of incoming air supply and the minimum width for the outgoing air. Looking at the side view, here we can see the minimum height for the incoming air supply and the minimum height for the exhaust. Early in a project, obtain the manufacturer's data sheets so that they can be compared and you are ready for the worst case scenario as to the maximum or minimum requirements. Here we see for a 2 megawatt the various air requirements. This particular design has 2 radiator systems available, an ambient temperature of 40 degrees C, 140 degrees Fahrenheit, and an ambient temperature of 50 degrees C, 122 degrees Fahrenheit. The selection between the two may or may not make a big difference in cost, but it will make a difference in the design. Here's a 2 megawatt generator with a 40 degrees C radiator. Here is a 2 megawatt with a 50 degrees C radiator. Side by side, we can see the physical difference between a 40 degrees C and a 50 degrees C radiator. When using motor operated dampers, make sure that they spring operate to open and motor closed. A lesson learned on a project, the contractor disconnected the circuits such that the motor operated dampers went to their spring open position. This was winter time, so to keep the room comfortable, they mechanically closed and locked them. Of course, this locking was not removed once the work was done, and the next time the emergency power supply system was needed, the vents did not open. The design should also consider the various elements of heat, cold, dust, humidity, snow, and ice accumulation around the housings, louvers, remote radiator fans, and prevailing winds blowing against the radiator fan discharge area.
Action!
Looking at our AFLAC, we'll focus in now on the fuel systems. So in our summary of Chapter 4, we talked about the different classes, and recall that's the minimum time the system needs to run without refueling. So we must size the tanks for the appropriate load and the appropriate runtime. Because of that, 7.9.1.3 tells us that we should size it also so that the fuel is consumed within the storage life of fuel. Now if you ask, you'll find that shelf life of diesel fuel is 6 months to a year, and definitely 2 years you better have done something with it. So if the fuel cannot be consumed, then there needs to be another means, say, to treat the fuel to take care of a stale or contaminated, or replace that stale contaminated fuel with clean fuel. Here we see a system where the fuel is being cleaned and returned to the tank. Visually, we can see what happens when we have oxidized fuel, and then it goes to various polishing from 40% to 80% to fully polished fuel. If there is a subbase tank, these subbase tanks are normally designed with baffles. So if we're trying to filter fuel, we have to somehow be able to take from one end of the tank and return back to the other. One way is to have ports on either end, or another way is to have ports on one end, but one of those are piped down to the opposite end of the subbase tank, giving you the ability to flow. The baffles are designed to allow fuel to go in between the sections. Fuel cleaning or polishing systems can be permanent, or shown here, can be portable and brought in to service and maintain the fuel. Here's a typical diagram that you might come across showing a main tank filling up a day tank and the day tank supplying power to the generator. A couple things I want to point out here is, one is the NFPA 110 7.9.4 says that a day tank on this diesel system shall be installed below the engine fuel return elevation. Here we see in the diagram where the generator is supposedly pumping that return fuel back up. Another comment is, ideally, that return fuel should be going to the main tank. Return fuel is heated. Heated fuel, like ambient temperature, reduces the kW or the horsepower of the engine capability. Here we see another diagram of an outdoor fuel tank. It has its tank filling inlet, also shows a fuel tank vent, and an auxiliary fuel pump indoors, bringing fuel from the main tank to the subbase tank. It also shows a overfill pipe going back to the main tank from the subbase tank. With outdoor enclosures, there may be a need to build a platform to allow access to the controls for the service and maintaining of the generator set. Here I have a shout out to the Cincinnati Fire Department, the nation's first career firefighters, established April 1st, 1853. The code discusses the fuel supply could be from natural gas or liquid petroleum. When the fire department arrives, they will go ahead and shut off the main gas supply to the building. This means that you must have your natural gas going to the emergency power supply ahead of that cutoff. There's also then a tag indicating that there is an existence of a separate emergency power supply, and the emergency power supply has its own shutoff valve. The gas supply to the emergency power supply, the prime mover, should be designed so that it's not inadvertently shut off. Sizing programs have the ability to help size the fuel lines, be it for natural gas or liquid propane, and some projects have both. So here we see we have 14 inches available from the utility and 11 inches are required by the generator set. We can select the different generators and see what the pipe size is required. At 13 inches we find that we have to increase the size from 3 inch to 4 inch. So we're being able to do some of these what ifs. Also at 370 feet, if we increase that to 380 feet, see our pipe size goes from 3 to 4 inches. So we're right on that edge of designing. So we can see by doing what ifs, we can go down to 4 inches pipe size and we can handle 12 inches at the supply side.
Action.
Going back to our AFLAC, let's look at the exhaust. Here we see a diagram of an indoor generator set with the flexible connector going up to the silencer, then going out through a wall thimble to the outside where either we have the exhaust going vertically out or horizontally. This generator set had the need to run the exhaust up above the roof line so that exhaust could not come back in through any of the open windows. The design is such that condensation and moisture would go straight down and not back to the silencer. Internal to the generator, the silencer is insulated, once again keeping the heat away. Sizing programs are available to help design the exhaust pipe if we want to run it away from the generator set. Here we see a 2 megawatt unit selected, and all the information for that unit is already preloaded into the sizing program. So we can do the various what ifs. A critical silencer has the information for the back pressure. If we change that to a hospital, the back pressure changes. Basically from a silencer that is critical to hospital, the silencer gets longer and so there's more back pressure. If we want, we can go to a user specific and be able to put in the back pressure required for that particular silencer. So we're going to go ahead and take a look at a hospital type silencer, put in a pipe length of 20 feet, and we see that our pipe size stays at 14. When we change the number of 90 degrees, that goes from 14 to 22 to 24 inches. So once again, we're able to do the what ifs, saying, hey, it is a short length, but we do have to add some elbows, and that definitely changed. The sizing program then gives a printout that we can put into the file that shows the generator information, the data that we put in, and a recording of the back pressure. Also remember, if you're going to add exhaust spark arresters, there is back pressure from those
Action.
as well. In returning to our AFLAC, we will now focus in on the acceptance test.
In order to streamline the process of putting your new equipment into service after it has been installed, it is important to go through a checklist to confirm all the equipment required has been received prior to the technician's arrival at your site. Your experienced power service provider will provide a checklist to be completed and returned to their appropriate service office. Installation will not begin until it is confirmed the set arrived with no freight damage, loose connections, and was completely as ordered. Both indoor and outdoor generator sets should be firmly mounted to a concrete foundation as specified by the manufacturer. The pre-startup checklist will differ somewhat for indoor and outdoor installations. Before the installation of an indoor set, it is important to check that all the loose equipment supplied with the set is there, such as the exhaust equipment. Indoor units must have the exhaust completely installed. Do not bend the flexible connectors section or use it to compensate for misalignment between the engine exhaust and the exhaust piping. An engineered thimble must be used where the exhaust penetrates the roof or wall. At the termination, there must be a rain cap on the vertical discharge. And on a horizontal discharger, there must be either a rain cap or the pipe cut off at a 60-degree angle with a bird screen installed. Outdoor units require the exhaust to be completely installed, including the rain cap, which must be able to open and close freely. Generator load conductors must be connected to the generator output breaker and the transfer switch if supplied. Generators generally arrive neutral bonded to the ground from the factory. If the system requires a solid neutral, then the jumper on the generator must be removed. It is usually from the ground stud on the main alternator to the neutral bar. Control wiring should be in a conduit separate from the load conductors. Start wires need to be a minimum of number 18. They need to be pulled up into the generator controller and to the connection point in the transfer switch. Utility power must be connected and available to the transfer switch. Do not plug the controller in. Building loads should be available. The transfer switch must be tested and powered down to plug in the controller. Power outages will occur during the testing of the transfer switch. Indoor installations require a cooling system duct at the radiator to be installed. Indoor installations require intake and exhaust louvers, and they have to be checked to ensure they're fully operational. Any fuel tank must have a pressure test before startup. The tank should be at least 75% full with number 2 off-highway diesel Supreme. Spark-ignited engines must be installed per the manufacturer's installation manual. Supply volume must be sized for 100% rated load. The gas volume requirement is supplied on the generator data sheet. If a block heater is supplied, it must be wired to the appropriate voltage, but not energized on startup. Any battery charger must be installed and wired. Installation instructions supplied should be studied before installation. If the battery charger is more than 15 feet from the batteries, additional sensing wires may be required. If the installation is required to conform with NFPA 110 installation, 3 additional wires must be pulled from the charger to the generator controller for alarms. If in doubt on any detailed checks, the generator power service provider should be consulted.
Testing. It is suggested that a thermal scan program be conducted. This establishes a baseline, plus any anomalies can be identified at the initial startup. A qualified individual will prepare a report. Let's discuss the mainline circuit breaker. Here we see where one mainline circuit breaker is on the alternator end of the generator set. This mainline circuit breaker has electronic trips and the ability to be padlocked. Multiple mainline circuit breakers may be put on the generator, and this is where a breaker may be located to feed a load bank. If feeding a load bank, consideration may be given to providing it with a shunt trip. Therefore, if the generator is being tested under load bank and there is a call from a transfer switch for emergency power, the load bank can be shunt tripped. Some suggested accessories are the alarm switch. Why would we want to put an alarm switch on the breaker? It is possible that the breaker will trip, and in an emergency running around, a tripped breaker may be confused with a breaker that is still on. The handle has partially gone down to the off position, and as you know, within your home, you have to take that tripped handle down to the off position and back up to the on position. Auxiliary contacts are used when we're doing multiple paralleling generator sets. With an auxiliary contact, we know the position of the breaker if it's in the open position or closed position. Here we see a multiple generator system lineup. Shunt trips can be used, as we already discussed, for a breaker feeding a load bank, again being able to open up that breaker if there is a call from a transfer switch for emergency power, thus dumping the load bank off the generator. Another application is with closed transition transfer switches. With the utility company approving a closed transition transfer switch, there's a need to put a shunt trip on a breaker either on the utility side or the generator side, just in case the closed transition transfer switch gets stuck connected to both sources. For that purpose, there's a timer which would then shunt trip one of the two sources, eliminating the two sources parallel. The overcurrent protected devices in the emergency power supply system shall be coordinated to optimize selective tripping of the circuit overcurrent protection devices when a short circuit occurs. Here we see a switchboard with a combination of insulated case breakers on the left and molded case breakers on the right. Trip adjustments can become very complex, and they can include some information data windows. A fixed time current curve is shown on the left, while on the right we can see the adjustability of having a trip element with various long time, short time, and instantaneous adjustments. In coordinating devices, we want to be able to show where there is no overlap, that is, complete selectivity coordination of the devices. Let's briefly review transfer switch types before we move on. Basically, there's the open, the delayed program, and the closed transition. This is a control interface for an automatic transfer switch. The blue button on the bottom right is to test the transfer switch. The standard transfer switch is an open transfer switch. It's a break before make. The load is either connected to the utility or the emergency power supply. When transferring between two live sources, there's approximately 100 milliseconds where the contactor is not connected to the generator or the utility. The delayed or programmed transition transfer switch has two operators. One controls the utility side, the other controls the generator side. Neither contactor is closed at the same time. Where with the open transition we had one operator and the disconnect time was approximately 100 milliseconds, with the delayed or programmed we can adjust the amount of time delay, that is, the load is not connected to either the utility nor the generator. The advantage to this may be the transferring of large motors. When in this neutral or off position, the motor has an opportunity to settle down, slow down, shut down before we go ahead and re-energize it. In the closed transition, this is also known as make before break, there are once again two operators as we had in the delayed transition style, but there is no mechanical interlock. the load will momentarily be connected to both the utility and the generator. There is a limited time where this is allowed, approximately 100 milliseconds. If the two sources are paralleled for longer than that, there's a timer in there that will cause a set of contacts to close, and either the utility side breaker or the generator side breaker is shunt tripped so that the two sources are no longer paralleled together. Utility approval is required to install a closed transition transfer switch. So why bring all that up? It's because when there's an existing facility and we're adding to it, we can do the acceptance testing by simulating an outage at least one transfer switch, or we can initiate opening all switches or breakers supplying normal power to all the automatic transfer switches that are part of the new emergency power supply system that's being commissioned. When using a test switch to simulate a power outage, there could be an in-phase monitor installed in that transfer switch. If the in-phase monitor function is turned on, it waits until the two sources are passively in phase. This commonly takes longer than 10 seconds. Authorities having jurisdiction must realize that the transfer switch has an in-phase monitor and the two sources are passively becoming in parallel, therefore don't expect a 10-second transfer. Let's monitor the transfer switch as we run a test using an in-phase monitor on the transfer switch. We're waiting for the in-phase monitor to come in. On the left we see the degrees difference and the frequency difference between two sources. As the numbers start to come down on the left, we are getting closer in phase and the time of transfer. It took 18 seconds for that transfer to occur. Another lesson learned was making sure there's coordination with the UPS technicians. If a UPS is in bypass, then it is seeing raw power and not going through the UPS. If there is a momentary power outage, the load loses power. Here's a diagram showing the UPS in bypass where the main supply is going direct to the critical loads. With the UPS in bypass, the rectifier and inverter can be removed for servicing and maintenance. Be sure to coordinate with your UPS technician. Acceptance testing begins with unit testing. That is right at the factory, getting the individual components tested. Then that leads to integration testing, followed by system testing, and at the top, acceptance testing. An example of unit testing is testing of the automatic transfer switch at the factory. Here we see a picture of the transfer switch switching mechanism. A commissioning agent was doing the acceptance testing of a 2 megawatt generator system. They found that an automatic transfer switch did not consistently transfer correctly. It would hang up. Upon further investigation, they checked with the automatic transfer switch factory. There had been a recall on a particular item. It was involved using a nylon washer versus a steel washer on the operating mechanism, and this recall had not made it to this particular location. It is recommended that a factory witness test be done at the paralleling switchgear factory. Ideally, the generator switchgear factory will have the paralleling breakers for testing, as well as control panels representing the generator controllers. Also, transfer switches and remote enunciators are there to complete the system testing. Preferably, have motor generator sets there, and not just utility 1 and another utility saying it represents the generator. Have actual dynamic engine generator sets to show how the system will react. To show how complicated what a simple system may look like, I took a look at a water treatment plant where we had 5 breakers, and when using these 5 breakers, there's a possible 32 different possible states of breakers being open and closed. It is preferred that there be one document used for the original submittal approval, the programming of the PLC, the factory acceptance test, the same document also at the site acceptance test, and then this be used as part of the O&M manual. In the 2016 edition of NFPA 110, there's a very simple statement, but it makes a dramatic change in how a system is accepted during acceptance testing. How a system is to properly parallel and the load shedding, load adding, the verification of that versus the system design documentation. Let's take a look at various paralleling schemes and see how they change from what I show here as a figure 100 through a figure 900. Now, basically speaking, figure 100, 200, 300, 400, and 500 are pretty standard designs, and most everyone will do these paralleling systems. It's when you step over into the figures 600, 700, 800, and 900 is where the big boys play, and it really takes a high quality engineering staff and also then the acceptance testing to be sure that what is being delivered on site is a requirement for the project. So even we may have what appears to be a simple 5-breaker scheme. Again, we said that has 32 possible states. We want documentation that says if this event occurs, here's the system's response, and also if an event occurs and there's a system response that is not appropriate, then what is the operator's actions? And all this documented for the O&M manual. So there's a load management system. How do we do the acceptance testing? And what is a load management system? The load management system allows the facility engineers to control when a load is added or shed from a power system. This makes paralleling systems more robust and improving power quality to critical loads on many power generation systems. We need to ask 4 things. 1, which loads need to be managed? 2, what is the load priority order? 3, how will the loads be shed? And 4, how is load shed coordinated? Once these have been defined and the system designed, we must then be able to test this under a system so that we are assured that the load management system functions as designed. In this chart here, we see the results of under frequency shedding. A motor is started and the frequency dips. A couple priorities are shed, allowing the voltage and the frequency to recover. The threshold is set at 59 Hz and the delay at 2 seconds. If the delay was reduced to 1 second, we could possibly see further loads shed that otherwise could have stayed on. Generator set manufacturers have white papers on load management systems. They can help identify load management system applications, setting up a load management system, and guidelines for 7 load management methods. When the emergency power supply system consists of paralleled emergency power supplies, the quantity of emergency power supplies intended to be operated simultaneously shall be tested, simultaneously with building load for the test period. So the challenge gets to be having a load test with building load when the building hasn't been loaded yet. So other loads need to simulate the intended load. To help simulate load, have the factory trained technicians there to simulate loads on the equipment and answer any questions during the testing period. Technicians can assist in the proper documentation during the testing period. And if necessary, do the immediate troubleshooting, maintenance, and repair so that the test can continue. Here we see weights being added to an elevator. The test period will continue for not less than 1 1/2 hours, and the runtime shall be recorded. The test load shall be all loads that are served by the emergency power supply system, so all transfer switches will be transferred over. As stated, the test will be for 1.5 hours, and that run time shall be recorded. The time delay on start shall be observed and recorded. The cranking time until the prime mover starts and runs shall be observed and recorded. The time taken to reach operating speed shall be observed and recorded. The time taken to achieve a steady state condition with all switches transferred to the emergency position shall be observed and recorded. The voltage, frequency, and amperes shall be recorded. Where applicable, the prime mover oil pressure and water temperature shall be recorded. When normal power is restored to the building or facility, the time delay on retransfer to normal power for each switch with a minimum setting of 5 minutes shall be recorded. The time delay on the prime mover cool down period and shutdown shall be recorded. The engine start function shall be confirmed by verifying the operation of the initiating circuit of all transfer switches supplying the emergency power supply system loads. The full load test consists of not less than 30% of the nameplate kW rating for the first 30 minutes, not less than 50% of the nameplate kW rating for the next 30 minutes, and 100% of the nameplate kW rating for the next 60 minutes. Less applicable derating factors for site conditions.
The worst time to discover your generator system has a problem is exactly at the moment you need it the most. Only running a generator under load will determine if it's able to perform and bear the load of a power outage. You want to be sure the standby generator set is capable of carrying its assigned load. Only loading the generator to its assigned load will verify this. Load banking is the process of connecting ancillary load to the generator system. The industry standard is to load bank with resistive power. This loads the generator section to 100% at unity power factor. Loading by switching the system load to the generator is not an adequate test. Only a simulated load bank test can ensure the generator system is loaded and tested to 100% of its rated capacity. Testing to 100% of capacity ensures the cooling system, the most frequent reason for failure, is working efficiently and attains the rise in temperature to test the cooling system and burn off harmful excess fuel and carbon deposits.
So let's do a little recap. To help us design a more robust emergency power supply system, we're using the acronym AFLAC, standing for Acceptance, Fuel, Location, Exhaust, Cooling. For acceptance, make sure the installation is finished. Notify the authority having jurisdiction. And why? For level 1 installation, the emergency power supply system will not be considered to comply until a final proof test for all the EPSS has been performed. Here's a summary of the testing requirements, plus a note that the one-step requirement has been removed. Here is a summary of everything that needs to be observed and recorded during the testing. It must be confirmed that all safety verifications have been performed. Here's a list of documents ready to have for the authority having jurisdiction when they arrive. Next on our AFLAC is fuel systems. We discussed diesel fuel, natural gas, and liquid propane. For location, we looked at indoors and outdoors. For exhaust, we looked at the back pressure requirements and the design of exhaust systems. We covered the cooling, heating, and ventilation of emergency power systems. And that's our AFLAC when looking at NFPA 110, Chapter 7, the Installation and Environmental Considerations. Thank you.